Okay guys, let's take a look at our lesson today. It's on curve sketching. So let's talk about curve sketching. The actual topic is a quite popular topic. You'll see it in calculus classes. Having a question on the AP test that only has to do with curve sketching is not going to happen. What you will have though is all these little different pieces. They would make a multiple choice problem, like they would perhaps ask you about the symmetry and Y-Intercepts, or maybe they'll ask you about asymptotes or derivatives, or other things to do with it, increase, decrease, concavity. You'll see all of this stuff on the test. It just won't be packaged as one big curve sketching thing. But that's what we're going to be working on in this lesson, is curve sketching. So we have several things that we need to consider when we are sketching without a calculator. Of course, this would be without a calculator. One would be symmetry. So let's talk about that one first. Really, they are very big on even and odd symmetry. They just are very big on that. For whatever reason, I mean, this is like a pre-cal or algebra 2 topic, but you will see, it's very possible that you will see references to symmetry on the test. So let's just remind ourselves, go over it. If we substitute a negative x into our function and we get the regular function back, then that is called even. If you remember that, that's even symmetry, which means that it is symmetrical across the y-axis. Okay, so that's even. If you take the original function and you put in a negative x and you get out the exact opposite of what you started with, then that is considered an odd function, and it has symmetry about the origin. Okay, has symmetry about the origin. So, and looking at our particular example, let's just do them one at a time. So symmetry. And for graphing, it's just helpful. If you know that it's symmetric, then it reduces your workload. If you know that the right side looks exactly like the left side, it's less to graph. So that's a reason why we would talk about it with curve sketching, is it might decrease your workload. So if I were to substitute a negative x in here, in this function, we know that cubed roots of negative x would still remain negative. This one, a negative to a first power, would still be negative. But what about this one right here? A negative to an even power would be positive, so therefore it's mixed. So there's no symmetry. It's not either. It has to be one complete way or the other. It has to be exactly like what you started with or exactly opposite. Otherwise, it has none. So symmetry is none. So let's look at the second thing they would be interested in, the X and Y intercepts. Gosh, we've been doing intercepts for years now, and I still have students that are a bit confused. If we want the X-intercepts, we make the Y 0. If we want the Y-intercepts, we make the X 0. Right? I mean, that's what we do. So for our intercepts, so we would, let's make the x 0. So if I make the x 0, then y is 0. So I have at 0, 0, there's going to be an intercept. It's actually x and y intercept. To find the x-intercepts, I'm going to set the function equal to 0. And in order to solve that, I would factor. I would factor out the smallest constant and the smallest variable, so x to the 1/3. So I'd be left with 2 plus x. Hopefully we know 4/3 minus 1/3 is 1. So I would have x is 0, which we already discovered. We know 0 is an intercept. We found it when we were looking for y-intercepts. And x is negative 2. So those are our intercepts. Okay, symmetry and intercepts are done. Asymptotes. Let's talk about asymptotes. There are 4 types of asymptotes to check for. Vertical asymptotes are where the denominator equals 0, if you remember from pre-cal. Horizontal asymptotes, we would take the limit as x goes to positive and negative infinity, and we would get them. If we're going to infinity and we're tending to 2, then I have a horizontal asymptote at 2. If we're going to infinity and we're tending to infinity, then I don't have a horizontal asymptote. So this is how we would find horizontal asymptotes in calculus. There was a different way we did it in pre-cal, but we would think about it in terms of calculus, so we'd want the limit. Slant and curvilinear asymptote. So slant asymptote is where my numerator is 1 larger. In other words, the degree of the numerator is 1 larger, you know, x squared over x plus 1. That would be an example of a slant. X squared over x plus 1, that would be a slant asymptote. Curvilinear is where the degree of the numerator is more than 1 larger. So x cubed over x plus 1, that would be an example of a curvilinear asymptote. The degree is 2 more than the denominator, so that would create a curvilinear asymptote. Now, no, you're not going to have to draw a curvilinear asymptote. It would just give you information as you're graphing that, you know, if the function is behaving strangely, you might be able to tell. It'll give you more information. Of course, you're going to have to find your first and second derivatives. But let's check this figure for all these asymptotes. So I don't have a denominator. I don't have anywhere it's undefined. So I don't have a vertical asymptote. So the asymptotes, vertical, none. If I take the limit of this going to positive or negative infinity, what's going to happen to my y value? It's going to approach infinity or negative infinity, whichever way we're going. So the limit as x goes to positive, negative infinity is that. So there are no horizontal asymptotes. Do we have slant or curvilinear? No, we don't have those either. There really are no asymptotes on this particular function. So that's our asymptotes. So now let's look at derivatives. We would do the first derivative to determine increase, decrease, max, and min. So our first derivative is 2x to the negative, 2x to the negative 2/3, then plus 4x to the 1/3. In order to find the zeros, I would factor that one. So 0 equals, of course, I'm going to factor out a 2, and my very smallest variable would be x to the negative 2/3, so I'm going to factor it out. That's going to leave me with 1 plus 2, let's see, 1/3 minus a minus 2/3 would leave me with an x. So my, now here's something important. I'm not going to rewrite it, but I want us to understand when I set this equal to 0, am I setting the numerator equal to 0 or the denominator? Denominator, right? Because it's negative. So we need to be very cautious. When I set this equal to 0, I'm actually not finding a 0. What am I finding? A singular point, undefined, right? These would be our stationary points. This would be our singular point. So just be cautious. You don't have to rewrite it as a fraction, but just know that when you find that, it is where the derivative is undefined. So I do my sign chart. I check my signs, and I get negative, positive, positive. So let's see what that means. So we're going to, we have a minimum. We don't have a maximum, do we? We have a minimum at negative 1/2. So we have a relative minimum at negative 1/2. Now when you put the negative 1/2 back into the original function, you get something a bit messy. It is negative 9 over 2 cubed root of 2. So we're graphing. We just know that that's just some weird negative number. I'm not going to expect you to know the value of that. We just need to know it's negative. Alright, so that's my minimum. I can see my increase, decrease off of here. So I'm not going to write out increase, decrease specifically. You can if you want to. But I'm just going to reference my sign chart for increase, decrease when I'm graphing. So increase, decrease. Alright, we have our min. So now let's do our second derivative. So our second derivative is negative 4/3 x to the negative 4/3 x to the negative 5/3. And then what? Plus 4/3 x to the negative 2/3. Okay, in order to well, we would set that equal to 0, and I would factor. So I factored a positive 4/3 out. Doesn't really matter. So I factored 4/3, and which is smaller, the negative 5/3 or the negative 2/3? The bigger one is smaller, right? Because it's negative. Negative 5/3. So, well, we want to factor the smallest one out, and that is actually the smallest one. And when we do that, we get negative 1 plus negative 2/3 minus a minus 5/3 gives me x. Okay, so when I set this factor equal to 0, am I finding a 0 or an undefined? I'm finding an undefined. And I do have an undefined at 0, and I also have a regular 0 at 1. So let's do our sign chart. And our sign chart is positive, negative, positive. And this is the sign chart for the second derivative, f double prime of x. So this one is going to give us concavity. And you can write out concave up, concave down. But we're just using it for graphing purposes, so you don't have to. Now certainly I've seen questions all the time on the AP test of where we're concave down, and you would actually have to, answer that question. But the reason we are finding all these things is for our sketch. So that takes care of derivatives, gives us a lot of information. The vertical tangent lines, so let's talk about vertical tangent lines. First of all, we have something weird going on here because this is a continuous function. There's nowhere that it's undefined, right? I can put any x, any value for x in that I want. But my first derivative has an undefined at 0. So we're continuous, but not differentiable there. So we need to think about what things would make us continuous and not differentiable. A cusp, or a corner, or a vertical tangent. Those are our three options. Now, we can actually discover what it's going to be by looking at increase, decrease. If it's a cusp or corner, is my increase and decrease, am I going to change from increase to decrease or decrease to increase? I'm going to change, right? Because if it's a corner, if it's a corner, you would be, oh, that's a horrible corner. If it's a corner, you would be coming up and then down, right? Or if it's a cusp, you would be coming up and then down. So you would have a change in direction, or a change in increase or decrease. Do we have a change in increase or decrease at 0? No. So that rules, basically it rules those out. It can't be that. So it has to be a vertical tangent. Does that make sense? So we're not using the second derivative test. We're using the first derivative test and the second derivative test. No, first derivative test and the test for concavity. The first derivative test tells us, since we did the first derivative test, because it never fails. Okay, the first derivative test doesn't fail. It tells us that there is no change. It goes from increase to increase here. We're not changing and going to decrease. So there has to be, because of this additional information, we have an undefined. We are continuous in the main function, but undefined on the derivative. That means that there's a vertical tangent there. So we do have a vertical tangent at 0, 0. Okay, we do. So, last task is to graph it. So let's use all the information that we gathered and let's graph it. We have, let's see, we have some zeros. We have a 0 at 0, 0 and at negative 2. We also have a minimum at negative 1/2. That weird, we're just going to say it's right there. Negative 1/2, negative 9 over 2 cube root 2. I'm just going to say that's where that is. I don't really have anything going on the right side, and I need a little bit more information. So an easy point to get would be at 1. So I would substitute a 1 up here, and I would get 9. So I would go ahead and plot that just so I have a little bit more information. All right, so let's piece this together. So I'm going to look at my first derivative. I'm decreasing until I hit negative 1. Okay, here's my negative 1. So I'm decreasing, so that means I have to start up, right, to be able to decrease. Okay, so I'm decreasing until I hit -1. I'm also supposed to be concave up. That's concave up. We okay there? All right. So from -1/2 to 0, I'm increasing. And let's see. I'm increasing. So I need to, there's actually, what do we have at 0 and 1? We have inflection points where we change concavity, right? I mean, they're not asking us for them, but just so that we're aware. So we are going to start increasing here to 0, and we are concave up, and we start increasing. Is everybody okay so far? Now at 0 we have a vertical tangent. You know, that's kind of hard to show in a graph. Vertical tangent just means you go straight up for just a moment. I mean, not very long. So I'm just going to draw it straight up right there. That's my vertical tangent. Okay, just, I mean, I'm exaggerating it so that we can see it on the graph. I'm exaggerating it. Now, from 0 to 1, we are concave down, but still increasing. So I need to draw it in such a way that it looks concave down, but I'm still decreasing. Whoops. Okay. Got a little carried away. Come on. There we go. So we are concave down, but we're still increasing. Is everybody okay with that? Oh, it's kind of weird, but we have to show concave down. Now after 1, we are concave up and still increasing. So I need to kind of turn it and make it look concave up and still increasing. It's not an easy one to graph, which is why I picked it. Okay, and that's our curve sketch. Okay? It's this right here. It's just where you go straight up. That would have a vertical tangent. Right, it goes through and then it goes up for just a moment and then it keeps going. It's a tangent. It's not, yeah, that you were thinking asymptote. It's not an asymptote, it's a tangent. A vertical tangent. In other words, my tangent line here would be straight up because my function is straight up. Okay, are we okay with that? So that's curve sketching.